Hello, it's Mr. Rika here, and I don't have a funny witch hat today, but I do have a cool robot arm. Ah! Okay, so I wanted to go through the study guide with you and explain it with you so that you can follow along. Alright, so this looks a little different. It's a little different format, but it's the same info. So the first question is asking you to circle the pair of forces that show the most net force. So the first question you have to ask yourself is, what is net force? So net force is when you combine all the forces to figure out what the overall impact is going to be on the objects. So we've got 4 different options here. We've got car A here on the left and car B on the right. The first thing I would recommend you do is kind of what I did here, is draw the vectors just showing the direction of the force, because I think that would help you then figure out what the net force is. So we first look at car A and car B. So I'm going to do some notes here in blue, even though the answers are in red. The net force of car A and B. Well, I know they're going in toward each other, so since they're going opposite directions, we need to cancel out whatever forces they're acting on each other so that we can figure out what the net is. So 30 on one and 20 on the other, that means there's a net force of 10 newtons. Okay. Oh, where'd that go? There you are. Oh, man. Okay, so the next one down, we've got the car is 20 newtons. Car A and car B has 5 newtons, so that leaves us with 15 newtons of net force. The next one down, car A has 10, car B has 7. That means we have 3 newtons. And then the last one, car B has 5 and car A have 5, both together. That means there is a net force of 0 newtons. Well, I don't know why this keeps disappearing on me. Bear with me. Alright, so when we look at these, we're looking for the one that has the most net force, and clearly that's going to be the second one that is circled. So I've labeled my diagram here with 20 newtons for both of those. So the next questions are, does it represent a net force of 0? Well, no, because we already subtracted those and we found it was 15, which leads to the next part, which is to draw the net force. Well, I have my 15 newtons here, and I've got my arrow or my vector. And remember, vectors show the strength, and which is another word for magnitude, and direction. So I've drawn my arrow going to the right because we know that car A has 20 newtons of force. It's the stronger force, therefore our net force is going the direction of the stronger force. So what's going to happen when the two cars impact? Will they stop completely or not? Well, no, they are not. They're going to move to the right because the forces are unbalanced. And just like we drew earlier with our net force of 15 newtons to the right, that's the direction that the cars are going to go. Next, we have some pictures here of objects, and we're drawing our forces, our vectors of the forces, to figure out what's going on and to make some free body diagrams. So we have our first one, which is an airplane going higher and faster. These are 2 key words. There goes that pen again. All right, so if it's going higher, well, gravity is always acting on the plane. We can see it by drawing this little arrow down here. Well, if it's going higher, then its lift has to be a stronger force than the gravity. So that vector is going to be bigger to show it's an unbalanced force causing a change in motion. So going faster, that's the other key word. We've got the words thrust and drag we've heard. Thrust is that forward pull, and drag is that air friction, pulling it back in the other direction. So we've got the bigger arrow here for thrust and the teeny tiny one for drag because it's going faster. So they have to be unbalanced to cause that change in motion. Next, we'll look at this stationary tether ball. Stationary is another word for not moving. So if it's not moving and its motion isn't changing, what kind of force is it? A balanced force. So we've got our 2 arrows. One is showing gravity. But there's got to be another force there to make it balanced, to make it not move, and that's that pull from the string up on the ball. The next one is a rowboat moving to the right. So if it's moving to the right, it's got to be an unbalanced force because it's changing its motion. So as it's moving to the right, we've got our other little arrow here showing the drag from the water, because sometimes drag is not just air, it can be fluids too. We've got our normal force, or buoyant force in this case, and gravity pulling down the boat, because gravity is acting on us all the time here on Earth. Now you might be thinking, well, I don't know if I'm getting faster going to the right or if I'm moving at a constant speed. So if you did think that, good job, because I wasn't very clear. So technically, if we're talking about the free body diagram I've drawn here, it's based on if we're moving to the right and we're getting faster. Oh, this pen's not going to work with me. Getting faster. All right, the next one we'll look at is this one here with the box. So you should have drawn a beautiful box, as you see here on the table. And we know that if it's not moving or changing, it is balanced. So now we look at the next dot down, which is gravity is an action force pulling on the box. So I've drawn that here, pulling it down to the earth. And then it says it needs to be at 100 newtons. Okay, so we've got our 100 newtons here for gravity, and we have to draw a vector showing the other force on there, because if we only had the vector for gravity, then we know it's an unbalanced force and the box would be falling. But it's not, it's just sitting on the table. So our other vector here has to be pulling up with the same, or pushing up in this case, with the same amount of force as the other gravity vector. So that's going to also be 100 newtons. Now we move on to weight and drag. Both of these are forces, and we look at weight. Weight is kind of another way we talk about gravity, and it's kind of weird to think about weight as a force, but it is. Now the other thing about drag is we talk about it as air resistance, but we can think about it as fluid resistance because it applies to water and other gases too. So an example of how drag could be helpful to someone or something. So if we're flying a kite, that's helpful. You need air resistance or else you don't have a beautiful kite to fly. A parachute, also equally important. You need a lot of air resistance for that to make it function properly so you don't just fall to the ground. And then flying a flag would be another great example. Otherwise it's kind of droopy hanging there and it's not wonderful at all. Okay, then we look at how drag can be a problem. Anytime you're in a vehicle, then there's and maybe even a boat in water, it's going to slow you down, and that's how it can be a problem. Okay, next we move on to this little girl on her scooter. So she's driving along and she tosses a ball up as she's moving. So we know she's going at a constant speed, and that's really important to note, constant speed. So you see here I've drawn her vectors and that they are equal and opposite. And we know that balanced forces get us to a constant speed. Another way to think about that is that their motion is remaining the same. Okay, now you can predict whatever your prediction was about where it would land, but I gave you a scenario to think about. So imagine you're on Earth, which I think most of us are, and you jump up down. Jump straight in the air and land right back in the exact same spot, right? So now imagine taking a ball and throwing it in the air. It would land in the exact same spot. Well, what if you were on a scooter instead? Well, you might be thinking, well, on Earth, I'm sitting still. But remember that the Earth is always rotating and revolving around the sun and on its own axis. But because we're going at a constant speed, it's going to appear as if we're not moving at all, kind of relative to us compared to the Earth. So if the girl's on her scooter and they're both moving at a constant speed, when she throws that ball in the air, it's going to land back exactly in her hand because the ball is traveling both at a constant rate with her and the scooter. It's a little bit confusing, but again, think about that analogy of Earth, that the Earth is always moving. If you jump straight up and down, and go ahead, you can try it right now, and you'd land in the exact same spot. So just kind of use that analogy to help you out. The next is a little bit of data analysis. So we have a car going on two different surfaces. The first one is no friction, and the second one is cement. And we have to figure out, well, what's the difference between these? Well, if there's no friction, obviously cement has some friction, and you know that cement's kind of bumpy. So we look at the data here, and the question asks, what happens to the speed of the car with no friction on the ground compared to cement? Well, a couple ways you can look at this. First, you might look at the data tables, and there are two data tables. It lists the units that they measure in, and then there are the graphs. And the graphs are kind of that visual representation of the data tables. So taking a look at those two, you should notice a pattern here with the slope. And you know from math class that slope is rise over run. And the steeper it is, the faster it's changing, which is true. So if you look over here at no friction, you can see there's speed listed down here. And for the cement car, or cement track, it's also listed down there. So when you compare those two and you look, well, you realize that in 7 seconds, this car got to 126 or so, and in 7 seconds, this one only made it to about 84 centimeters. So that's pretty significant difference, and that tells us that it accelerates or changes its speed more quickly on the no friction surface. The second part to this is what would happen if there was equal friction to the applied force moving the car. So there's this push from the car, and there's this push back from the friction from the ground. So if the car is already moving, what kind of motion is going to happen? Well, we know if it's equal, it has to be a balanced force, and therefore it's going to maintain its speed. And we saw that video about the skydiver, and we know that when the gravity in the air reach that terminal velocity point, that skydiver maintains that speed that they were traveling at. So same thing applies on a horizontal plane. We have a car going down the street. Okay, our next question is actually 4 little scenarios. And you need to make sure you can understand how different objects are going to behave based on their free body diagrams and what we know about balanced and unbalanced forces. So you see this little gymnast girl, and she's just standing there waiting her turn. Well, what's going to happen? She's going to stay still or stationary, and that's due to her balanced forces. There's nothing that's pushing her or pulling her more one way or the other. Next, we have this guy on a motorcycle, and as he stops his engine, it says there's only friction acting on the bike. So what's going to happen? Well, eventually he will slow down and stop because there's more of that opposite motion or opposite force instead of that push force. There's no more push force, there's just that opposite force, so he's going to eventually slow down and stop. The next one is this airplane flying at 100 miles per hour, and the force of thrust equals the force of drag. You may have been like, well, wait, hold on, what's thrust, what's drag? So thrust is that forward push, and drag is the back push from the air, because there's air all the time impacting us, and especially when they're going fast and they're flying through the air. But if it's the same and it's equal force, then the airplane's going to travel at that 100 miles per hour and maintain it because of balanced forces. Next, you look at this guy climbing up the stairs, and there's more applied force than friction. So we've got an unbalanced force scenario. Because there's more push than more of that slowdown force, which is friction, there's going to be an increase in speed. All right, so last but not least, first let me apologize because this picture was a little hard to work from on your notes, your study guide packet. So I'm going to draw it here because it's a little clearer to see. And I'm actually going to draw it directly on the diagram, which I also agree would probably have been a lot better to see. So I'll do it with red pen so you can see it a little better. The first scenario is asking us to draw a vector or right no motion of car A from the point of view of the person H watching it go by quickly. So here's person H, and here is car A. So, oh, there they went. There they are. So if person H is standing there and they're watching car A, just imagine, close your eyes for a second. What would it look like as if they were zooming past? Which direction? Well, to person H, it would be going in this direction. And I drew my vector really long because person H is standing still, so the car is going to be seeming to go very quickly by. Now, what I wanted you to do was to replicate the direction of that arrow over here. Okay, the next one asks you to look at tree G, which is right here, and compare it to the motion of car B. And here's car B. Well, tree G is standing still. We'd assume it's not moving. Kind of weird if it was. And so car B is going by quickly. So to car B, this tree looks like it's moving backwards, and it looks like it's moving backwards very quickly. So we would take that arrow and draw it here to represent that. Next, we are supposed to look at car C and look at look at the tree G from the point of view of car C. So car C is going the same direction as car B, but they're going slower. So when I imagine what that would look like, I'd still see the tree going backwards, but this time it's going to seem as if it's going a little bit slower. So my vector for that would be same thing here, but just a little smaller. All right, last two here. We're going to look at, oh, there are my letters. All right, so we're going to look at the motion of car C compared to B. So again, they're going the same direction. But if you were to imagine it, close your eyes. You're driving there together, and you're looking over your shoulder, and you're looking at the car next to you. If you were car B and you're going faster, it looks like car C is going backwards. But because they're still pretty close in speed, the vector is going to be pretty short because it only looks like it's going backwards just a little bit. So we draw our vector like that. Last but not least, we're looking at car D and car F. They're both going the same direction. We're kind of pretending here. And they're both going the same speed. So if they're going the same speed and they're going the same direction, just imagine, look to the person next to you. You're both probably sitting in a chair. And if you're sitting in a chair next to each other, I'd say, well, what's the motion of the person next to you? You'd say, no motion. Well, the same thing applies if they're both going the same direction and the same speed, as long as it's a constant speed. So we would say it's no motion. Okay, sorry that was a little bit long. Hopefully that was helpful for you, and feel free to send me a message or talk to me in class, and I will help answer any questions that you have. Good luck studying.